I want to finish up the unit on some discussion about reactions in metal complexes. So metal complexes can do a lot of reactions. You've already seen some in organic chemistry through like your palladium coupled or your palladium catalysis couplings and other ones. So, we'll talk more later on in units on redox chemistry, which is next, and maybe some kinetics. We'll talk about some reactions then. So I just want to kind of give like a brief discussion of some definitions that you might come across if you ever read more about coordination complexes. So we'll focus mostly on ligand exchange. And so I guess one question is, how do ligands exchange? So we'll talk a little bit more about this in our kinetics unit, but there are multiple possible mechanisms that you could imagine for why or how things happen, so mechanistically. So we could imagine one would be dissociative. So suppose that we have some 6-coordinate metal, Ml6. So what I mean by dissociative would be that first you could lose a ligand, and then we could have our, let's say L prime, our second ligand come in. So this is the dissociation step, right? So dissociation. And then we could then have our metal with 5 of the same ligands and then have L prime. So that would be a dissociative mechanism. We could also have an associative mechanism. And this happens quite often for, let's say, square planar ML4 complexes. So we could add L prime, and then we end up with a 5-coordinate complex. So this could be the trigonal bipyramidal, for example. Prime, and then we would then lose L, and then you would get to ML3, L4. So whether we go through either one of the mechanisms, it's hard to know a priori unless we know some more about the complexes. So if you take, for example, graduate organometallics, they'll talk more about this. We won't talk about it any further. We can distinguish this through some kinetics experiments. We'll talk a little bit more about this in a couple units. But for now, there's multiple ways that we could. The end result is the same, right? We've still substituted one of the blue ligands for a yellow ligand, but there's multiple pathways. So that's just something to keep in mind. Okay, some further definitions. So these are just like the final end products, right? So ultimately, if it happens, it might be thermodynamically favorable. It could be unfavorable if it doesn't happen. But what we don't know is a lot of these things are also kinetics effects, so how fast things are happening. So some definitions that you might come up in the literature, for example, would be something could be labile if ligand exchange is fast. There aren't any really hard and fast definitions. Sometimes people say maybe like around a minute. I would say, so like in your body, for example, often metals are often labile because you want things to come on and come off for your biological processes. And this comes, like around like fast timescales, right, on the order of seconds. And then on the other hand, if ligand exchange is not fast, then it's called inert. Slow to ligand substitution. So I want to talk about these differences in definition, labile versus inert. This does not govern stability versus unstable, right? This doesn't tell us about whether the ultimate end product is favorable delta G. So an inert reaction could still be favorable thermodynamically, but what we're talking about is that it's slow. So this is a kinetic effect. So we'll talk about further on in additional units. So labile versus inert. But one way that we can think about these things is, so for example, I'll give you an example of a labile reaction. So if we take hexaaqua copper, and then we add ammonia to it, this reaction is very fast, and we usually form So even though it's in equilibrium, we end up forming copper with 4 bound waters and 4 bound ammonias, 2 waters, and 4 waters as the byproduct. This reaction goes really fast because copper 2+ is labile. On the other hand, if I think about something inert, if we take cobalt 3+, and we try to add, even acid to it, this to end up with, let's see. Okay, yeah, so we add excess water and ammonia or hydronium. You should, in principle, protonate off the ammonia. Ammonia is more basic than H+, and we should end up with the hexaaqua cation and maybe also ammonium. So this, even though this is actually thermodynamically favorable, so delta G is less than 0, this is actually a very, very slow reaction. So because cobalt 3+ is inert. So cobalt 3+ is inert, copper 2+ is labile. So let's talk about why that is. So a lot of it has to do with the idea of the LFSE, and also if you think about octahedral complexes and the nature of the d orbital splitting. Let's first talk about LFSE. So LFSE, we've talked before about different configurations that and the different energies of the LFSE. So let's see. If you have a high LFSE, basically, it's going to be more inert, right? We talked about that. That gives extra stability on top of whatever electrostatic attractions your metal has to the ligand itself. So let's see. So based on LFSE, we should know that inert complexes are often going to be D3 or low spin D4 through D6. And then, let's see, for labile, it's going to be high spin D4, D5, D6. And also if you have more electrons, so D7 through D10. So these are more labile. So it's again, like D10, of course, we know has no LFSE. And then high spin D4, we have that extra, or is less because we're going across that delta O. Okay, so that's the way to think about it through LFSE. Another way to think about it is if we think about an octahedral d orbital splitting diagram, right? We know that T2G and EG, this is metal ligand sigma star. And then for sigma only ligands, this is non-bonding. So if we're cobalt 3+, so it's low spin, cobalt 3, we're D6, so low spin cobalt 3+, right? We have no electrons in the ML sigma star. We have them in the non-bonding orbitals. So as a result, we're not weakening. We have really strong metal ligand bonding. In comparison, if we think about our copper 2+, we're D9. So we have 3 electrons in these ML sigma star orbitals. So the more electrons you have in these EG orbitals, we're basically weakening that bonding between the metal and the ligand, which makes it more prone to substitution, right? So the ligand more easily come off if you want to think about a dissociative mechanism. As for why this low spin cobalt 3+ is extra inert is because even though the T2G is non-bonding, what we've also done is now we've occupied empty orbitals, so it's harder for an associative mechanism for a ligand to come in and bind before then dissociating another ligand. So these are all factors to consider. So the one thing I really want to keep in mind is, again, populating these sigma star orbitals really changes the nature of our metal ligand interaction, and the T2G, the non-bonding, wouldn't. On the other hand, if we have pi or pi star ligands, like pi donors or pi acceptors, that might also affect the occupation of the T2G when we're thinking about the lability or the inertness of those ligands. What else did I want to say? Oh, and then one last thing was 4D and 5D transition metal complexes are often much more inert than 3D for reasons of bonding. It's again the strength of your metal ligand bonding. And we said that before that 4D, 5D, those orbitals stick out more, they have stronger interactions with ligands. So these are all things to consider when we're thinking about the reactivity of the metal for ligand exchange.